Okay guys, in this next video we're going to be talking about enthalpy, which is a state function, and also we're going to be looking at thermochemical equations. So the question at the top, how does the heat flow in a chemical reaction relate to the internal energy change of the system? And the answer is it depends upon the path. For isochoric conditions, that is conditions under constant volume, there's no work done. And in that case, if you take the first law expression, delta U equals Q plus W, if there's no volume change and there's no PV work, then the heat flow in the chemical reaction is identical to the change in the internal energy. And an example of this would be in a bomb calorimetry experiment where the volume doesn't change because the steel bomb container is so rigid that the volume can't change. And so when you measure the heat flow in a bomb calorimetry experiment, what you're really measuring is delta U. For chemical reactions that are open to the atmospheric pressure, pressure is constant, not volume. And in that case, when you go to calculate the heat, you can't neglect the work because the volume of the system can change. When you have isobaric conditions, the external pressure is equal to the system pressure, and if you plug in the minus P external delta V expression for the work, then you get an expression like this for the heat, which is not the same as it is for the isochoric path. This quantity here is a new state function. It's actually the change in the enthalpy of the system. And so that's what enthalpy is all about. It is a way of connecting the measured heat under isobaric conditions to a state function. And we're going to call this state function the enthalpy. The formal definition of enthalpy is that it's the internal energy of the system plus the quantity, pressure times volume for the system. And it's a new state function. It's an extensive property, which just like internal energy, if you double the size of the system, you'll end up doubling its enthalpy. It's measured in units of energy, joules or kilojoules. It's similar to energy, but there's a correction factor involving the pressure-volume product for the system. And just once again, the reason why we care about enthalpy in chemistry is because when we do our chemical reactions under isobaric conditions and we measure the heat flow for the chemical reactions, the heat flow is equal to the quantity delta H. It's loosely connected to internal energy, but it's slightly different. So since most of our chemical reactions are carried out under atmospheric conditions, the heat that we measure is equal to the enthalpy change of the reaction, which is this symbol here. The change in the enthalpy associated with the chemical reaction. That's what the subscript R means. So this is the primary quantity of interest often in thermochemistry, and right now what I'm going to show you are what are referred to as thermochemical equations. These are chemical equations that include the enthalpy change for the reaction. I'm going to point out that there's a subtle difference between thermochemical equations and stoichiometric equations. Previously we learned that stoichiometric equations can be interpreted at both the microscopic level of molecules and also the macroscopic level of moles. Thermochemical equations are really meant to be interpreted only at the mole level, only at the macroscopic level. And in this sense, we're allowed to have fractions as our stoichiometric coefficients. Previously, we learned that the convention for stoichiometric equations is not to include fractions in the coefficients because it wouldn't make sense to, for example, have 1/2 of a hydrogen molecule. However, it does make sense to have half a mole, and so you are allowed to have fractions when you're talking about the mole level only. And sometimes in certain thermochemistry applications, we need to have fractions. Okay, so we have to allow ourselves to work with chemical equations in thermochemistry that have fractional stoichiometric coefficients. So here in this first example, I have a reaction for sodium and water to produce sodium hydroxide and hydrogen gas. Here is the enthalpy of reaction for this reaction. The negative sign means that it's an exothermic reaction. Notice what happens if I divide the reaction by 2. So I reduce the subscripts by a factor of 1/2. I also divide the enthalpy of reaction by half as well. Phases are very important in thermochemistry. They make a difference. So here we have the reaction of hydrogen gas and oxygen to produce water vapor. It has a given value of delta H, again exothermic. But if you change the phase of the product, if you instead form liquid water, you'll see that the enthalpy of reaction is different. It's not the same. So phases make a difference. We are also going to be manipulating thermochemical equations algebraically. Just like we did up here, we multiplied one equation by a factor of 1/2. When you do that, you make the same change to the delta H value for the reaction. In some occasions, we are going to have to reverse a thermochemical equation. That is, we are going to exchange the reactants and the products. That is equivalent to multiplying the chemical equation by -1. And you do the same change for the enthalpy of reaction. We'll also be adding and subtracting thermochemical equations to one another, and you do the same thing with the enthalpy of reaction. We're going to see some examples of this as we move forward. So in this first example, we're simply being asked to write out a thermochemical equation given a paragraph describing the chemical reaction. So let's practice writing thermochemical equations. So in this first reaction, we have aqueous sodium hydrogen carbonate solution. So testing our nomenclature skills, sodium hydrogen carbonate. It's aqueous. It reacts with hydrochloric acid, HCl, aqueous, to produce aqueous sodium chloride. We're also producing water. Let's see, I'm going to go ahead and make that liquid. And then there's one more product, carbon dioxide gas. So we want to check to make sure this is balanced, and it looks to me like it already is balanced. That's great. And then it says the reaction absorbs 12.7 kilojoules of heat, which means it's an endothermic reaction. And so the delta H value for this reaction is going to be positive, and it's 12.7 kilojoules. Okay, so this is the thermochemical equation for part A. For part B, we're dealing with hydrazine, N2H4. That is the product, and then it looks like the nitrogen. Let me check real quick. So the propellant for rockets is obtained by mixing hydrogen and dinitrogen tetroxide. These compounds react to give nitrogen gas and water vapor. So our reactant is hydrazine, it's a liquid, and dinitrogen tetroxide, also in its liquid state. The products are nitrogen gas and water vapor. And we'd want to make sure that this is balanced. Let's see, we are going to need 4 oxygens. So the oxygens are balanced. We are going to need now 8 hydrogens. So we're going to have to put a 2 here. And now we can balance the nitrogen here. We've got 4, 5, 6. So 3 moles of nitrogen gas. This is a exothermic reaction. It says the reaction evolves 1024 kilojoules. So delta H is going to be negative. 1024 kilojoules. So that's the thermochemical equation for part B. Here we're going to be doing some manipulating the thermochemical equation. So we have the thermochemical equation for producing liquid water from its elements. They want us to write this equation for 1 mole of liquid water. So what I'm going to do is divide that equation by a factor of 1/2, or by a factor of 2. So we're going to have H2 gas plus 1/2 O2 gas, giving us 1 mole of liquid water. And in order to calculate the delta H, we need to divide the delta H that we have by 2. And so I'm getting delta H for this reaction is minus 286 kilojoules. In the follow-up step, they want us to take this reaction that we've just written down and reverse it. So instead of doing the formation of liquid water, do the decomposition of liquid water. So that's equivalent to multiplying the chemical equation by a factor of minus 1/2, a minus 1. And if you multiply the chemical equation by minus 1, you need to do the same thing to the delta H value. So it's going to be plus 286 kilojoules. So if you reverse an exothermic reaction, it becomes an endothermic reaction. Likewise, if you reverse an endothermic reaction, it becomes an exothermic reaction. Let's see, so here in this problem, we're going to be thinking about another thermochemical equation. So this is the reaction of methane with water vapor to produce carbon monoxide and hydrogen gas. It's an endothermic reaction. We see that the delta H is 206 kilojoules. They say the reverse reaction has been explored as a way to prepare methane. Which of the following reactions are exothermic, and of these, which of them are the most exothermic? Well, part A is just the reaction that we have right there, and so reaction A is still endothermic. Reaction B, they're simply doubling the coefficients, and so it's also endothermic. In fact, the delta H would be 412 kilojoules. Part C, they have reversed the reaction, so part C is going to be exothermic. They've simply reversed the reactants and products, no change in the coefficients, and so the delta H will be minus 206 kilojoules. In part D, they've doubled the coefficient, so it's exothermic. The delta H would then be minus 412 kilojoules. So as written, part D would be the most exothermic. This problem shows us that thermochemical equations can be used in stoichiometric problems. So here we have a reaction producing ammonia from nitrogen gas and hydrogen gas. The reaction is exothermic. The delta H is minus 91.8 kilojoules. They want to know how much heat is evolved when 9 times 10 to the 5th grams of ammonia is produced. That's quite a lot of ammonia, so this is probably going to generate a lot of heat. So what we're going to be doing here is converting from grams of ammonia to moles of ammonia, and then we can use the thermochemical equation to calculate the kilojoules. Okay, let's see how that works. So 9.07 times 10 to the 5th grams of ammonia. We are going to need to divide by the molar mass. I'm going to take that to be 14, 15, 16, 17, 17.0 grams per mole. And then I'm going to use the thermochemical equation. For every 2 moles of ammonia that are produced, you're going to make 91.8 kilojoules. And you get a large amount of energy. Over 1 million kilojoules, over 2 million kilojoules are produced. But that's a lot. That's a large amount of ammonia. That's industrial scale right there. Let's do another one. Part B. How much heat is evolved when 10 grams of hydrazine reacts according to this reaction? So here we're going to convert from grams of the hydrazine to moles of hydrazine, and then we're going to go to the kilojoules using the thermochemical equation. So we'll start off with our 10 grams of hydrazine. I'm going to calculate the molar mass real quick. So roughly 32 grams per mole. And then I'm going to multiply by minus 2,048 kilojoules for every 2 moles of hydrazine that react. So the grams cancel, the moles cancel. We're going to be left with kilojoules. I'm getting minus 640 kilojoules out of that. Okay, so you can use thermochemical equations to calculate the energy produced from a given amount of reactant or from a given amount of product produced. You can use thermochemical equations just like you use stoichiometric equations. With that, I'm going to go ahead and stop this video, and we'll pick up the next one with Hess's law.